case the other one doesn't work. Okay. There we go. So we have zinc, solid, with a 0 charge, going to zinc, 2 plus, plus 2 electrons. Where do the electrons go?
Into the sulfur and into the Cu2 line. No, into just a Cu.
Electrons do not dissolve in water.
So don't they move through the water?
So electrons do not move into the salt bridge. Part of this cell is missing. What part is missing? The what? The wire. Okay? So there would be a wire, la la la, la 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 la, wire. Okay, and the electrons go that away. Yes? Okay. So the electrons go that away, and the zinc comes off. And over time, what do you notice about the overall charge here? We have 2 minus, 2 minus, 2 minus, so that's 6 negative, yes? And we have 2 plus, 2 plus, 2 plus, 2 plus, 2 plus, 2 plus, 1, 2, 3, 4, 5, 6, 12 positive. Uh-oh. Does nature like a buildup of positive charge?
No.
No. So, how do we fix this? Well, we're gonna hold up on that for just a second, and we're gonna go over to the other side and see what's going on over in the copper half cell. Now, if you remember, in the copper half cell, were we going from metal to ion or ion to metal?
Ion to metal.
Ion to metal. So we had Cu 2 plus 2 electrons became Cu solid. That process has already taken place here. So I'm just going to draw like a little ghost Cu2 plus that's no longer here, okay, because it got used up. Okay, that's a little ghost Cu2 plus. It didn't turn out very well. I'm sorry. I'll make the 2 actually a 2 plus. There we go. Okay. This one is gone. Okay. So what do we have in this beaker? We used to have some Cu2 pluses, but we don't anymore, right? No Cu2 plus anymore, or at least less of them. So what is left now? Only SO4 2 minus left. So what is the overall charge?
-2.
The overall charge is -2, -4, -6. Does nature like a buildup of negative charge?
No.
No. Nature hates a buildup of charge, whether it be positive or negative. Nature wants everything to be neutral, electrically neutral. All right? How could we get some negative charge over onto this side because we have too much positive? And over on this side, we have too much negative. How can we fix that?
Can you carry the negative particles and positive particles?
We can. Where could we get some extra negative particles to fix our too much positive problem over on the left? Where could we get those from?
Salt bridge.
Yeah, from the salt bridge. We're going to take those chlorides from the salt bridge, and they're going to move in there to neutralize the extra positive charge. So the Cl minus ions move from the salt bridge into the zinc half cell, and they neutralize the excess positive charge. So we used to have too much positive, but the chlorides can come in and say, no, no, I'll neutralize you all. So they just start moving in there. How about on the other side? Yeah, the NAs are going to move in. Okay, so the Na moves into the copper half cell. And that will neutralize the excess negative charge. Isn't that nice? Because now we can actually have this process take place. If that were not present, the copper 2+ ions would not form copper solid. The zinc atoms would not give up their 2 electrons because we cannot have that imbalance of charge. Okay? While we are here, what the heck is that thing at the end of the glass U-tube, at the end of the salt bridge? What's that thing? That is a cotton plug. I'm going to go see if I can find a U-tube. Look at that. That's a U-tube. Now, if I have some water, yes? That's not water. Yes, it is. Oh, I don't know. I'm just going to throw it out and rinse it, just in case it wasn't water. Pretty sure it's just water because I haven't labeled it. Now, if I fill up this U-tube, yes? Now, let's say I need to get this thing turned upside down and into my 2 beakers. So here's my 2 beakers. And if you can't see, please feel free to like stand up or move closer or whatever. All right. What's going to happen? Now it's like empty here because it all falls out. You can fix that problem by putting a cotton plug in there, okay? The cotton plug will prevent the water from just falling out, all right? It's not going to keep it in there forever. Eventually it would start dripping, but you're not going to spend forever turning it over and putting it into the solutions, right? It keeps it in there long enough that you can do that. Okay, so that's why we need that cotton plug. So literally, it's just like a cotton ball and you just shove it in there. Okay. And yeah, that looks pretty good. So let's now move on to our next page and take a look at what's happening. So you can see here, it's showing the sodiums moving out to neutralize the sulfates over here. And you can see the chlorides moving out to neutralize the zincs over on the left. And if you are on your phone, then you have a problem with your priorities. Okay, so what is the function of a salt bridge? The salt bridge allows for the migration of ions. What is migration? Movement, okay? Between the half cells, which allows a charge balance. What does it mean for the charges to be balanced? Neutral. To be maintained. So that's one way of describing the function of a salt bridge. The other way to describe it is to take the word migration and make it into movement. And it allows for electrical neutrality. Okay, so those are different ways of saying it. Now, before we move there, let's go back up here and take a look. What process is taking place at the copper electrode? Remember, we have copper 2 plus 2 electrons goes to copper solid. What is that half reaction called? That is a reduction. And if that is reduction, that means that the copper electrode is the something ode. Cathode. Okay. Fat cat. Also, red cat. What takes place at the cathode? Reduction takes place at the cathode. So you can also add red cat to your vocabulary if you want. All right, so we got our red cat there. And so the copper electrode is the cathode. What kind of ions are these sodiums that are moving towards the cathode? Those sodium ions are what kind of ions? That is a what kind of ion? That is a cation. And where is it moving? Towards the cathode. Cations always move towards the cathode. That is actually why the cathode is named the cathode. That's how it got its name. So if you're like, why is it named a cathode? Because that's where the cations go. And what's happening on the other side then? Who's moving towards the zinc electrode? What kind of ions are those? That's an anion. And what's the process taking place over here? Oxidation. Oxidation. and oxidation takes place. Zinc electrode is the what ode? Anode. So we're starting to build a vocabulary, like a consistency around this, right?
Yes.
So the cations move towards the cathode, the anions move towards the anode. And what are we missing in this diagram? Remind me. We're missing a wire. So why don't we draw in a wire? And what's moving in the wire?
Electrons.
Electrons. Which direction are they going?
Towards the cathode.
They're going towards the cathode and away from the anode. That is the direction that electrons always move. They always move from the anode to the cathode. Why can I not write the letter A without it going all goofy? Always move from the anode, because oxidation is losing electrons, to the cathode. And if you forget that, electrons move in alphabetical order from A towards C. From A to C. Is good? Okay. So, cations always move towards the cathode. Anions move towards the anode. And even the ones that are, like, let's say we have zinc down here, okay? That's part of the zinc sulfate solution. It will eventually make its way into the salt bridge, and it might even migrate over to the other side. But the ions move very slowly, so that's going to take a long time, okay? So we're really relying on the sodiums to go and replace the copper that is turning into copper solid, okay? Now, the sulfate over on in the copper half cell will actually move up into the salt bridge and also make its way towards the anode, all right? But like I said, maybe it'll eventually make it to here, maybe it'll make it to here. It would have to run for a long, long, long time to actually make it all the way over to the zinc half cell, okay? And of course, the electrons flow from what to what? From anode to the cathode. And you know what the nice thing is? If you know any one of these things, you can figure out all the rest, right? If you know electrons flow from anode to cathode, you can be like, well, where did those electrons come from? They came from the anode, which means the anode must be losing electrons, which means that must be oxidation happening there, right? And you're like, okay, well, they moved from the anode to the cathode. Oh, the cathode must be gaining electrons, so that must be where reduction takes place. And if reduction happens, then if I got electrons flowing into here, that's going to attract those positively charged ions, right? So the cations are going to move towards it. This thing is losing electrons, it's going to become a little bit positive, and so it's going to attract negative ions, so the anions move there. So it's all interconnected. Once you know one thing, you basically know them all. Another way to think of it, apparently AP does not like this explanation, but I don't know what your college professors will think. Yes? They may think this is a good explanation. I thought it was a good explanation for years. It's more like a physics explanation. Yeah? If you have electrons that are trying to flow, but electrons cannot dissolve into water, how are the electrons going to get from A to B? How is charge going to flow if there's no connection? You see how there's no connection there? There's no complete circuit. It's as though you've got this circuit and the switch is open. Yes? There's a gap in the circuit. By putting that salt bridge in, it's like you're closing that switch, right? Now, when the electrons get to here, the electrons can't flow, but the negative ions do flow. Okay, so we have a complete path for the flow of electrons and negative charges. Which direction are the electrons flowing in this diagram? Are they flowing clockwise or counterclockwise?
They are floating this way, clockwise.
Clockwise. Okay, so in this diagram, the electrons flow clockwise. Now, are the electrons always going to flow clockwise? No, it depends on which side. Like if you were to take the whole thing and just turn it around, they would flow counterclockwise because, you know, you're looking at it from the opposite side. But in this case, they flow clockwise. Which direction would cations flow? Cations would flow counterclockwise. All right, so like I said, your university professor is going to tell you what you need to know. I always liked it. Completes the circuit. How can it flow if there's no place for it to flow? But AP apparently is not happy with that explanation anymore. So maybe nobody is. Who knows? At any rate, this is just another diagram. I thought it was kind of pretty. Okay, so there we are. Alternatives to a salt bridge. The only reason I'm showing you these is if you see a picture of them, I don't want you to get scared and say, what is happening here? Okay? The normal cell that you'll be responsible for drawing looks like this. You've got the two beakers, you've got the salt bridge, you would have two sticks of metal and a wire connecting them. Okay? However, you might see a picture like this with a single beaker, but a single beaker that is divided, or maybe it's not a beaker, maybe it's a plexiglass container, yeah? And across that plexiglass container, they have this little thing you can slide in, and it is a porous barrier. What does it mean to be porous? To have holes in it, yes. Porous things have holes. I've lost my pen. I've lost my mind. There it is. Okay. So porous has holes. Tiny holes, the ions can slowly move through. So it is still separating the copper ions from the zinc ions. Because if you had copper ions over here, what would happen? They would just grab the electrons from the zinc right away, and you would end up with the electrons not flowing through the wire. Now, the nice thing is that once this is all connected up, the copper ions are actually being dragged towards the copper electrodes, so they won't tend to migrate the wrong way across the salt bridge. They want to move towards the copper. Okay, so that helps keep them separated. So all you need is to slow down the movement and you'll be good. Okay, you can also have a porous disc. They actually make beakers that are connected to each other like that, and they have a porous disc in the middle. All right, and it functions in the same way. And if you're feeling like you don't have a lot of money to spend on glass U-tubes, you can use a piece of filter paper or even a piece of paper towel what you would do is you would roll up this paper towel and you would soak it in a salt solution. I'm just going to use water for now because it doesn't really matter. You can't see the salt anyway. Okay, so let's imagine that this has salt in it, and I would then put it into each side of the beaker, and now I have a salt bridge that's just made of paper towel. Yeah? Cheap, right? Easy. Can find it at home. So if you wanted to make your own thing at home with some, cups and paper towel, in theory, you could do it. You would just need some chemicals to work with. Okay? What else could we use? We could also use a porous cup. So over here, we would have 1/2 cell. The whole thing would be made of that porous material, like some sort of clay, where the ions could eventually move through it. So we would have 1/2 cell in that porous cup. Ions could flow through that porous cup from 1/2 cell to the other 1/2 cell. Is good? Okay. You will not be responsible for drawing those things. You need to be able to draw like a little YouTube salt bridge and whatever, but I want you to recognize what the heck's going on here. Don't worry about this. This is cell notation. That's for AP because they do a lot more cell notation, and I just didn't want to bother like reformatting the whole thing. This is Tyler's summary, okay? That's Tyler's summary. My summary is down here. The anode is where oxidation occurs. The cathode is where reduction occurs. You can add in red cat if you want to. I always just use A and O are both vowels and C and R are both consonants, but whatever works for you. Electron travel is alphabetical from A to C. And where do they travel? They travel through the wire. Cations, they go towards the cathode and they move through the salt bridge. Anions move towards the anode and they move through the salt bridge. The anode loses mass as the solid metal are oxidized to the ions. I don't know if this is a good way to remember it. The smaller word gets smaller. Anode only has 5 letters, cathode has 7 letters, so the larger word gets larger. Or you can remember fat cat, right? The cat gets fatter, the cathode gets heavier. But whatever you like, okay? Or you can just be like, I understand how this works, and I understand that oxidation is taking place and I'm losing those metal things, and like, do you know what I mean? You don't need to use all these little tools if you don't need to. You should be able to describe the function of the salt bridge. What is the function of the salt bridge? Tell your partner. Why do we use a salt bridge?
And so that lets the building charged up with positive and negative and neutralize.
Thank you.
Oh,
What does the salt bridge allow? Movement of ions. And why do we need those ions to move? To balance out the charges, to maintain electrical neutrality. Either one of those language things will work as an explanation. Okay, good stuff. You should know, although you don't have to write it, you should be able to recognize it, the simplified cell notation. Okay, do you remember that from last day? Maybe not. Maybe.
Oh, yeah.
yes.
Yeah? The anode goes on the left and the cathode goes on the right. It goes in alphabetical order. Okay? This separates the two half cells. The anode reactant goes here, and the anode product goes here, right? It lost 2 electrons, or an electron. The cathode reactant goes here, and the cathode product goes here. So the cathode reactant is always the ion. The anode reactant is always the solid. And you know what we call this? That's our ion sandwich. The ions go in the middle. Will this work for all cells? No, only if you've got like a metal, metal ion, metal, metal ion. Okay, we'll look at some cells later that are a little bit different from that, but for now that'll do. And let's say you are called upon to draw a galvanic cell, a voltaic cell, an electrochemical cell. You will need to have how many beakers?
2.
2. How many different electrolyte solutions? 2 different electrolyte solutions. How many electrodes?
2 electrodes.
2 electrodes. What is an electrode? It's a stick of metal, okay? We'll talk a little bit more later about you can actually have, as long as it's a stick of something, it doesn't have to be metal, but we'll talk more about that later. You need a wire. You need a salt bridge. The thing in the salt bridge has to be soluble and it has to be unreactive. Let's take a look just really quickly at nitrate. NO3, NO3. What does it need in order to react? Nitrate needs hydrogen in order to react. We don't usually have hydrogen, so potassium nitrate is a good choice for a salt bridge, but sodium chloride's also pretty good. Okay? There we go. You need to have the ends of the salt bridge plugged with cotton balls. And in order to prevent a short circuit, you should always have either a voltmeter or a light bulb in your cell. Although it makes me a little sad because the voltmeter should be connected in parallel, but we connect it in series because we're just being lazy and just drawing it in there. Pretend I said nothing. That was a physics reference. Okay. Yeah. All right. So for the rest of class, I'm going to finish marking your quizzes because I'm almost done. Okay. And you guys are going to do pages 80 and 81. Now, there's a couple of corrections I need to make here. The CU should actually be MG. Okay. I made a mistake. So that should say MG. Yeah. There's one other thing I need to change for you. So on our second page, this language, thermodynamically favored, if something is thermodynamically favored, that means it is spontaneous. If something is thermodynamically unfavored, that is non-spontaneous. You guys are getting some of the AP terminology in here because they no longer like the language spontaneous and non-spontaneous. They prefer thermodynamically favored, which is really irritating to write because it's so long. And obviously 10B, don't do 10B because you don't know anything about Gibbs free energy unless you've taken some bio. And even at that, you don't know about it in this particular context. So yeah. Okay, so pages 80, 81. I will check that tomorrow for completion marks. basically what I'm going to do with these completion marks is I figure if you are here every day and you do all your work, I'm going to be like, here, have a percent. Okay?
Is it 8%?
A percent, 1%, which is actually very substantial for just showing up and doing your work. Do you know what I mean?
Yes.
So, but I do have people who are like, oh, which is fine, they can still get their grade. Right there.
It's fine. I'm done. Solve this.
Hi. Yeah, of course. You are doing pages 80, 81. Oh, sorry.
Like these are like these Yes, I want to do that. Unless I'm not in this part, hopefully. Yeah. Okay, so I'm right. Then it sync, right? Yeah.
Yes, of course. Okay, so based on this, you want these two to be the reactants. So this one is going to go that way, which is reduction. It's
Okay.
not the cathode.
Okay.
This one's going to go that way. And that's going to go that way.
Oh,
There you go.
thank you. Well done. Every time you for some.
Please feel free to come and ask me questions if you want to. I'll be done marking in just a moment or two.
Perfect, we did that. Okay, well, oh my God. Yes, I'm getting
Okay, I have good news. Most of you know what you're doing on reduction and oxidation, the redox quiz. If you don't, I also have good news in that you can retake this one quiz this one time because it is a skill, just like in grade 11. If you had me for grade 11, I let you redo things if you were lacking a skill so that you could master that skill. I only have one rewrite, but you can do one rewrite, okay? So feel free to either, if you feel like I have learned it since then, you could do it tomorrow during flex, or if you want to take the weekend to review it, you could do that. I will say one thing that cost a lot of people a lot of marks was they forgot to do this. What is that? Redox reaction, you split them into half reactions, and then you balance the half reactions separately. Then you make the electrons in equal the electrons out. You add them back together and you cancel things out if you need to. Okay? If you're feeling like you look at your quiz tonight and you don't know where you went wrong, please come see me tomorrow during flex. I can sort you out so that you can redo your quiz if you need to. I'm just going to total these up and enter the marks, and then I'll get them back to you. Okay? Thank you. Okay. Okay, what have I got here? I have
What process takes place?
okay, Juan. Grace. Kaya. Aaron. Samira. Yeah. Ryan. Go. Jinya. Do you want on? Michelle. Jonathan. Kukulin.